Okay, so we continue with our discussion on random vectors. So previously, we have discussed the linear processing of random vectors. So what are our conclusions? So if X is a random vector, with, let's say, mean mu X vector and covariance or autocorrelation, doesn't matter, matrix, let's say Cx, okay, then A times X, let me call this Y, is also a random vector. This is also a random vector. Now, how do you characterize this random vector? Well, you can characterize by its PDF. But let's assume that I only know its mean value and covariance matrix of this random vector. So can I say something about the mean vector and the covariance matrix of this Y vector after transformation? Indeed, what we have seen is expected value of Y is, this is the Y vector, let me have a capital Y, is equal to A times mu X. Then covariance matrix of Y is equal to A times Cx times A transpose. Okay, that is it. Well, these are very easy to show. So for example, for this one, you just insert, I will be doing this for Ry, expected value of Y times Y transpose. Okay, but Y is equal to Ax. So instead of here, I have Ax over here. For this one, I have X transpose times A transpose because of this transpose. Then I move this A out, move this A transpose out. So in between, I have X times X transpose. That is Rx. If you include means, it will be Cx. Okay, that is basically our result. This is the important case. So if this is Gaussian distributed, well, we are in luck, because Gaussian distributed is jointly Gaussian distributed vectors are totally characterized by mean vector and covariance matrix. Then, after transformation, is totally characterized by these two quantities over here. Now, what if these are for real valued cases? So, for complex valued case, let me write a note, complex valued case. Well, let me write it over with red then. Cy is equal to A times Cx times, so what's your guess? This is A Hermitian this time. Because for the complex valued case, we have the Cy definition as Y times Y Hermitian. And if you apply this, you get this one, okay? Y times Y Hermitian. So because of this Hermitian, you get over here this. And of course, Cy matrix should be Hermitian symmetric. If you take the Hermitian of Cy, you see that it remains Hermitian symmetric also. So I need Hermitians at this point. Okay. Now, let me discuss decorrelation of random vectors. Okay. So what do I mean by that? So given a random vector X, let's say, with Rx matrix, autocorrelation matrix, our goal is, I'm assuming that, again, zero mean vectors. Our goal is, expected value of X is equal to 0. Our goal is to find a T matrix such that Y is equal to T times X vector has a diagonal covariance matrix. Covariance, or as you see, autocorrelation matrix. As I have said, in signal processing, the random variables are in general taken as zero mean quantities because the mean corresponds for our purpose in general the signal itself. We explicitly write the signal and add the noise terms next to it. So those noise terms are the random quantities, and because of that, random variables in our problems, they're almost always zero mean quantities. Okay. So what's our goal? Now I would like to do a transformation, something like this, but at the end of the transformation, Cy should be a diagonal matrix. Okay. So we will see different methods of doing this. So number one, so this is called diagonalization by eigendecomposition. Okay. Well, I'm given Rx, isn't it? I'm given Rx. So can I write Rx as in terms of eigendecomposition? Would you agree with this? I'm writing Hermitian. If this is complex valued, then I have this Hermitian over there. So what's the meaning of this? Previously we have studied this. So this E matrix is E1, E2, I have En vectors. So these are the eigenvectors. Okay. What's the meaning of this? Then Rx times, let's say Ek, is lambda k times Ek. So this is the eigenvalue-eigenvector relation. So since this is a Hermitian symmetric matrix, I know that these vectors are orthogonal vectors. So this is an n by n matrix. So these are n-dimensional n vectors which are orthogonal to each other. So this E matrix is an orthogonal matrix. Okay. So that is the meaning that E Hermitian E, so these are n by n matrices, is equal to E times E Hermitian is equal to identity. Okay. Because as I have said, they're orthogonal vectors. So this is the inner product, again the Gremlin matrix. So it's equal to, since they're orthogonal, this is equal to the identity matrix. Okay. I'm assuming that these vectors are normalized to 1. Okay. So they're orthonormal. It's an orthonormal set. So how about this matrix? So this is the diagonal matrix of eigenvalues. Lambda 1, lambda 2, lambda n. Okay. That is it. So in general, well, we have such a fact. If I have an M matrix is E, if it is diagonalizable, E inverse. Okay, this is for general diagonalizable matrices. But Rx is special, meaning that it has Hermitian symmetry. So this is equal to, in our case, E Hermitian, because of this orthogonality. So actually this is the E inverse. So I have such a result. Okay, now this is what we know from our, let me see, earlier discussions on matrices, eigenvalues, and eigenvectors. Okay? So what should I do next? Now, if I let t is equal to, I'm just letting t be what? T is equal to E Hermitian. Okay? If I let t is equal to E Hermitian, then y is equal to t times x. Am I right? Y is equal to t times x. Then ry is equal to t times rx times t Hermitian. Am I right? This is our previous finding on autocorrelation this time. Okay, I'm assuming zero mean quantities. So if I do this, I have E Hermitian. So what is Rx? Rx is this, E, this matrix. So T Hermitian is E itself. Okay. So as you see, now I can move this bracket away. So these two cancel out. These two cancel out. So I get this matrix, which is a diagonal matrix of eigenvalues. So this is lambda 1, lambda 2. I have zeros elsewhere, lambda n. Okay. So I see that the matrix that I am looking for is actually formed by, you know, this eigenvectors, T matrices, something like that. Well, that is the end of this case. But let me have some more intuition on this case. So previously, at least for the 2D case, let's say that my x1, x2, so this is x vector times Rx times x Hermitian. Okay? I'm trying to sketch this is a function of this vector. So it is concentric ellipses, as you see. Okay? Again, the level curves. So as we have said, previously we have discussed this, there is a major axis and there is a minor axis of these ellipses. Okay, major and the minor axis of this ellipse. So this is for x. So an arbitrary random vector. Of course, entries of this vector is correlated, as you see. Well, how about this, the final result? In the final result, so this is for y. Y transpose Ry, y. Am I right? Now let's look at the quadratic product. So if I check this, level curves of this, so this is, let's say, y1, y2, okay, after this transformation. So what we see is that these are the ellipses that we have seen previously in the last lecture. Because if I write this one, this is equal to right now y1 square lambda 1 plus y2 square lambda 2. Am I right? So if I equate this one to, let's say, r square, just some number r square, then this is r over lambda 1. This part is minus r over lambda 1. This is r over lambda 2. This is r over lambda 2. Something like that. Okay? So details are not important, but as you see for this one, this matrix, the axes are aligned with, as you see, major axis of the ellipse is aligned with the y-axis, y1 axis, and the minor axis aligned with the y2 axis. Over here, in the original case, they are not aligned. Okay. So what's going on? So how can I do this alignment? Well, the reasoning is very simple actually. Now, so over here I'm trying to sketch this f of x. X times Rx times x Hermitian. Am I right? Oh, this is over here. Are there any other mistakes? Okay. So I'm trying to sketch this x Hermitian. So let me write this eigendecomposition over here. E, this, and I have E Hermitian and x. So as you see, I'm calling these as my y's. So this is my new y vector after this transformation. Y is equal to t times x, where t is equal to E Hermitian. Okay, this is my y vector. So this becomes my y Hermitian, as you see. So what's the meaning of this? Well, you see the following. Y is equal to E Hermitian times x. Okay, but I can take the inverse of this matrix and move this y over here. So from here, I can write E times y is equal to x. Okay? Or I can write the following: E1, E2, En times, I have y1, yn. I have an identity matrix over here, times, let's say, x1, xn. Okay? So what I see is the following when I look at this. Now I'm defining this axis as, let's say, y1 axis, this axis as y2 axis. Okay, I will explain it a little further. Now a point over here, let's say, can be expressed in terms of canonical basis, meaning that its first entry is x1, second entry is x2. Canonical basis is composed of the vectors whose columns of this matrix is, identity matrix is canonical vectors. Okay? So columns of this identity matrix is the canonical basis. So these are then the expansion coefficients, as you see. So the same vector can be also expressed as in an alternative basis using these eigenvectors. Then these y's are nothing but the expansion of this point in the alternate basis. So this is the alternate basis. Okay? So that is it actually. So what we see is that if I express an x point in the alternate basis with eigenvector basis, so this y vector is the expansion coefficient. So these expansion coefficients, for example, for this vector, it will be the combination of these two vectors, this one, and maybe I have maybe something like this vector and this vector. So I have combination of these two. Okay? So in the alternate basis, where y is equal to E Hermitian times x, so this becomes the change of basis matrix essentially. Change of basis matrix. And these are the expansion coefficients. Okay? X is the expansion coefficients of this point in the canonical basis. Y is the expansion coefficients in the eigenbasis. Okay? So once I do that, if I express this point in the blue basis, blue colored vectors, then what I see is that I get this diagonal covariance matrix. And this is what I want. Well, why this is important for us? This is important for us from statistical purposes, because if this covariance matrix is diagonal, we see that these random variables are uncorrelated with each other. Okay? So you don't have to, uncorrelatedness, actually they mean something. Previously we have discussed that. What is the meaning of uncorrelated? So uncorrelatedness means that they have no linear dependence. So they are not, easily predictable from each other in a linear sense. Okay, we will further describe it later on. So uncorrelatedness is not as strong as independence, but it tells us something that we are weakening the dependence between these random quantities by this operation. Okay? So this is method number one, diagonalization by eigendecomposition. So we have seen how this works. Now let me have a brief, twist on this. Okay. Diagonalization by unitary transformation followed by just scaling. Okay. So this is our second topic. Now, I will do the following. My T matrices, I'm just writing the result. Okay. So I'm just making, transformation matrix T is defined like that. Let then y is equal to t times x, okay? Then ry is equal to t times rx times t Hermitian. Then, well, this is e Hermitian rx. Well, let me write rx also. E so again, as we have done previously, these two cancel out. So of course now this is and this is cancelling each other. So at the end I get this identity matrix. But maybe we should mention what our intention with this. Now my intention is this matrix is lambda 1 times minus 1/2, lambda 2 times minus 1/2, or this is 1 over square root of lambda n, as you see, 0, 0. Okay, so this is my omega minus 1/2 matrix definition. Okay, since this is a diagonal matrix, you know, it's only affecting the terms on the diagonal. Okay, this is, maybe you can remember from earlier courses, this is called a function of a matrix, but this is again a definition how you do this. So for diagonal matrices, it only affects the terms on the diagonals. Okay, very good. So what we see is that if I do my transformation with t is equal to e Hermitian, in other words, if I switch to the eigenbasis, okay, what is the eigenbasis? Autocorrelation matrix has eigenvectors E. If I switch to that basis, so in that basis, in that representation, I have decorrelation. So uncorrelated random variables, elements of the vector, they are uncorrelated. If I also do the scaling, so this is first step. If I also do the scaling, this is just multiplication by some number. So first decorrelate and then scale. Okay? So there's an x vector. After this, it's decorrelated and then it's scaled by this. So I get identity. So what are the level curves for this one? Now for the level curves for this one becomes, as you can imagine, circles. Okay, this is further convenient. Okay, so level curves. After, you know, after t, let's say, after t mapping. Okay, so this is y1, this is y2, level curves of this. So I'm thinking about the quadratics, maybe I'm thinking about Gaussian distribution. So this is the Gaussian distribution's level curve, so this is a peak over here, and there are circles, and so on. At the cuts of this, I see circles. Now what else? I have a third method. This is number 3. Diagonalization by LU decomposition. So maybe we should remember what LU decomposition is. So L, A matrix. So this is a lower triangular matrix, L, lower triangular. So this is an upper triangular matrix. Upper triangular matrix. This is called an LU decomposition. This is a fundamental fact. Maybe you have seen this decomposition in Gaussian elimination discussions and so on. So how can I do this? Well, let's say that A matrix is something like this. A, B, C, D, E, F, G, H, I. So let's say that this is my A matrix. Okay. So how can I find this LU decomposition? Well, you do the following. Now, you multiply. So do you remember Gaussian elimination? You want to make this term 0. And you don't want to touch anything else. So first row stays the same. 1, 0, 0. If I multiply this, first row stays the same. So I want this entry to be equal to 0 after multiplication. So how can I make it 0? If I multiply minus d over a 1, 0, so this times this, as you see, minus d over a, this and 0, so I get 0 over here, and 0, 0, 1. I don't want to touch this part. So after this operation, what do I have? I have ABC, first row. This one, I have 0 over here. Am I right? Minus d plus this 0. I have some numbers over here. I have some non-zero numbers. Some, let me say, numbers over here. I, j, k, let's say. Then this part is g, h, I. Okay? So I don't want to calculate this, but I can also calculate it as you see. This number times b plus e is equal to this. Okay? That is it. So as you see, by calculating this L1 and multiplying this from left by L1, I have this 0. So you repeat this process. A sits over here. You multiply by L1, you get this 0. You multiply by L2, another one. So you get A, B, C, 0, M. Sorry, this is J, K. You have 0, L, M. Okay? You have this. Now you go on. You multiply by L3. Maybe you have 0, one more 0 over there. You multiply by L4. Now you have 0, 0 over here. Okay? Now, as you see, I have lower triangular matrices on the left. These are all lower triangular matrices. So their product will also be a lower triangular matrix. Okay, it will be also a lower triangular matrix. So this is an upper triangular matrix. So we are almost done. Then you can say that then A is equal to, so let me say L on left, let's say, on the left side. On this left side, inverse times, let me call this U. So this becomes, after these operation, an upper triangle. Well, this is JKI. What was this? I. So I don't want to keep this one. I want to keep it. So I have 1, 2, 3 zeros. So this is not present. Okay. That is it. So A is equal to this inverse matrix times U. So inverse of a lower triangular matrix is also a lower triangular matrix, and then I'm done. A is equal to L times U. Okay, so this is interesting. So how can I make use of this fact in my calculations? So how can I make use of this fact? But before that, let me show you this. If I have a matrix 10, 0, let's say 5, 20 to be explicit. Now its lower triangular part in this decomposition will be this. Something like that, 20. Okay. So as you see, this is the L part, this is the U part. Okay. Actually, this is diagonal, but at least this is not lower triangular. So this is diagonal matrix. It's both lower and upper triangular. Okay. So I have such a case. Now let me mention this. So if I have this kind of a lower triangular matrix, lower triangular matrices with ones on diagonal are called unit lower triangular matrices. Okay. So you may say, for example, let me show them by LU. There is a U, units. Okay. LU times I have a U over here. Okay. That is it. Now, clearly, every lower triangular matrix, which is not, well, I can always scale. So, for example, I have 10, 5, 0, 1. I have a lower triangle matrix like this. So how can I make this lower triangular? Now I can multiply this by 1 over 10. Then the first column will be multiplied by this. Then 1 over 2. Then 0, 0, 2. So this is identity, as you see. But if you do this multiplication, well, you get the first row. This is multiplying the first column. So I get 1, 5 over 10. Then this is multiplying the second one, 0 and 1 times 10, 0, 0, 2, something like that. So by doing this kind of an operation, you can always get a lower unit triangular matrix. Okay? By doing this kind of a very simple operation, I can always make these terms on the diagonal equal to 1 by scaling the this column by 1 over 10, by scaling the second column by 1/2. I can easily do that. Okay. So then what's going on? I'm erasing this. Then let's say that I'm an expert in this kind of decomposition. So if I have Rx, if I apply this LU decomposition on Rx, then what happens? Now you can say that there will be a lower triangle matrix, there will be an upper triangle matrix. So how about this? Well, this is Hermitian symmetric. Okay? Let me write. Since Rx is equal to Rx Hermitian, okay, so in order for the Hermitian symmetry to occur, what do I have? So this is always possible to write. This is a fact of linear algebra. Not for Rx, I can write it for almost any A matrix. Okay, there's some issues, but for any A matrix. So this is always possible to write, but in addition, it has to satisfy this. Now, since this is, then U is equal to L Hermitian. There is no other way around, okay? Because lower triangular matrix Hermitian becomes upper triangular and it satisfies this. Then this becomes L times L Hermitian. Okay. You can of course discuss it from the uniqueness of decomposition and so on. Okay. Because R Hermitian also has an LU decomposition and so on. There are issues, but this is the general idea. Now also every L lower triangular matrix can be written as unit lower triangular times a diagonal matrix, as we did a few seconds ago. So this is L is equal to unit lower triangular times a diagonal matrix. Okay. So now the Hermitian of this, well, this is diagonal LU Hermitian. Okay. So this is LU D Hermitian times LU Hermitian. So I get such a result. Okay. So this is a diagonal matrix, obviously, with, as you see, real valued entries because of this Hermitian right now. Okay. LU Hermitian. Now how about this idea? I select my T as LU inverse. So I do this operation, find my LU, or I apply LU decomposition on Rx, then I find its lower unit triangular part, then I take its inverse as my T. Then y is equal to T times X, then Ry is equal to, so what's your guess? LU inverse Rx LU inverse Hermitian. Okay. but it is equal to this. So if I substitute Rx over here, LU's cancel on the left. How about on the right? This is the Hermitian, and this is the Hermitian. So can I exchange inverse and the Hermitian? I can. So this becomes D times D Hermitian. So it's a diagonal matrix. Okay? If it is, diagonal matrix. If it is real valued, D times D transpose is equal to D square. Okay? For real valued. Real valued case. Okay? So what do we see? Now we see the following. Oh, you may ask, am I allowed to take the inverse of this matrix? Well, it is this kind of a matrix. So as you see, this has always unit determinant. So you can always take the inverse of this matrix. And it's easy to calculate that, the inverse of this matrix is also lower triangular, and so on. Now, here's a fact. So LU inverse is also a lower triangular matrix. That is, LU inverses, it's something like this. Let me see. This is 1. Let's say alpha, beta. Let's say gamma. So this is alpha 1, beta 1, gamma 1. So this is alpha 2, beta 2, some numbers. 1, alpha 3. I think that's enough. Or let me have one more. So this is all 0, this part. So this is our transformation. Okay? This kind of a transformation. So unit lower triangular. L inverse is also a unit lower triangular matrix. Well, why? Well, that is the case actually. Now, what is interesting is, now y is equal to this kind of a matrix. So this is the matrix, times x1, x2, let's say I have over here 4 of them, x3, x4, okay? This matrix times that. So what do we see? If I do this product, this is equal to x1, this is equal to alpha x1 plus x2, this is equal to beta x1 plus alpha 2 x2 plus x3, gamma 1 x1, beta 2 x2, alpha 3 x3 plus x4. So this is the vector. So this is my y vector. So this is the entries of this y vector. y1, y2, y3, y4. Okay? So what do we see? Let's assume that this random vector is, these are the samples collected in time. So this is first sample, this is after t seconds, some sampling period, second sample, third sample, fourth sample, and so on. So what do we see? Now this is like a causal, a causal combination, let's say. A causal combination of elements of x vector. X vector, okay? Why do I say causal combination? Because y1, in order to form y1, I only need x1. To form y2, I need x1 and x2, not the future samples. To form y3, so I need all the samples up to x3, okay? So you may see that this kind of a decorrelator. So again, this is achieving this decorrelation. it's acting like a causal decorrelator. Okay, so this is a little bit different. But again, this is establishing this decorrelation. After the application of LU inverse, again, what do I have? Ry. This Ry will have a diagonal, as you see, maybe D square, covariance matrix or autocorrelation matrix, as you see. Okay, so that's all for this hour. We will continue next time with more discussions.